So this is one of the questions given in your worksheet. Spring constant is given 200 Newton per meter. It's a 4 kg block. Now, when the spring is at natural length, the block is hit with a hammer such that it starts moving to the left with a speed of 4 meters per second. Okay, are you all able to imagine the situation? Initially, assume spring and block were both at rest with the spring at relaxed length. Now you hit the block starts moving. Okay, first question. What happens to the block after it is struck by the hammer? Comment on the forces that it experiences and what happens to its speed. Anyone? It starts moving with a speed 4 meters per second. What happens after that?
Where it experiences spring force towards the right.
Correct. When the block starts moving to the left, it will compress the spring. Okay, the next moment itself, the spring will get compressed a little bit. When the spring gets compressed, it will start exerting a force to the right. Now see, the moment the spring gets compressed, the block starts experiencing a force to the right. That doesn't mean it will start moving to the right. Okay, it has some momentum, right? Due to this velocity, it has some momentum in the leftward direction. The force exerted by the spring will decrease that momentum first. That 4 meter per second will become 3.5, 3, 2.5, 2, so on, as the spring gets compressed more and more. Okay, so just a moment, let me draw you the diagram and show. Okay, from that natural length position, where is the spring? Right. So from that natural length position, as the spring gets compressed, okay, due to the block moving to the left. Why is this not working? Okay, never mind. Huh. So once this happens, once the spring gets compressed, it will start exerting a force to the right. And due to that force, what will happen? The speed of the block will decrease first. It won't immediately start moving to the left. Maybe the speed becomes like something like 3 meters per second. Okay. But it still has speed. So it will continue compressing the spring. When the spring gets compressed a little more, okay, that force will keep acting on the block. So the block speed will keep on decreasing. And as the spring gets compressed more and more, the force on the block increases. The spring force becomes stronger and stronger, and the block's velocity decreases further. Finally, it will stop somewhere. Is this part clear to all of you? Were you able to imagine this happening? Okay. So that's the first part of the question. Next, will the spring force oppose the motion of the block or support it? Initially, it will oppose the motion of the block. Then, if the speed of the block decreases, find out the exact compression of the spring when the block speed becomes 0. Okay. So as the block experiences spring force to the right, it will slow down, and stop somewhere. You have to find out where it stops. Like at what compression of the spring X does the block stop? And hint is also given to you, apply work kinetic energy theorem. We know the initial velocity of the block, so we know its initial kinetic energy. And we know that it comes to rest. So we know its final kinetic energy as well. Okay. So if you write the expression for work done is equal to change in kinetic energy, you'll be able to find out the compression from there. One of you tell me, as the block moves to the left, what all forces act on the block?
Spring force.
Is that the only force acting? I'm just asking which forces act on the block.
Weight and normal.
Weight and normal also will be acting. Okay. Surface is smooth. So weight will act, normal force will act, and spring force will act. Okay. Pawan, you tell me, as the block compresses the spring, which of these forces do work on the block?
Sir, spring force.
Okay. Why will weight and normal force not do any work?
Sir, they are in vertical direction.
Correct. Displacement is in the horizontal direction. Weight and normal force are in the vertical direction. Angle becomes 90, so they won't do any work on the block. So work done by all forces is basically equal to work done by the spring force in this case. And that must be equal to the change in kinetic energy. Okay. One of you tell me from what we discussed in the last class, how do we calculate work done by spring force? What is the formula for spring force? Anyone?
K into X.
Okay, spring force is Kx. And last class we had solved some problems where we found out the work done by spring force when the spring is compressed by a little bit or when a stretched spring is released, such cases. So basically what we do is this, force is Kx, displacement will be dx, and there will be a minus sign because force and okay, force and displacement may be in the same direction or opposite direction, never mind, but dx is opposite to ds. Okay, dx and ds are negatives of each other, so we got an expression like this, and we need to integrate this from initial compression, how much ever that is, to the final compression or elongation, how much ever that is. That will give us the work done by spring force. Okay. So let's use that formula here, or you all do it. Integral minus kx dx from initial compression or elongation to final compression or elongation should be equal to change in kinetic energy is written this way, half m v square minus u square. Okay, I'll just mention all the values here. K in this problem is given 200 Newton per meter. All values are in SI units. Mass of the block is 4 kg, I think. Yeah. Initial speed is 4 meters per second. And you have to find out the compression when the block stops. So final speed is 0. Calculate final compression of the spring. And remember, initially, the spring was at natural length. When the spring is at natural length, how much is the initial compression or elongation? Anyone?
Sir, 0.
0. Okay, x initial is 0, x final is what you need to calculate. Can be done from this. Complete this, all of you. Make it fast. Any answer?
Sir, can you show the question? I just joined.
This is a worksheet question.
Oh, okay, sir.
Here I got x square equal to 2 by 25.
X square equal to 2 by 25. It could be. Could be. We'll see. Okay. See, it's just integration from here onwards. Minus k minus 200 I'll put aside. Integral x dx is x square by 2. Substitute limits 0 to final value of x becomes half. Mass of the block is 4 kg. V square minus u square. Initial speed is 4 meters per second. Square it becomes 16. Okay. 200 by 2 is 100. So minus 100, and when you substitute limits, it becomes x square minus 0. Substitute the upper limit in place of x, it's simply x square. Lower limit is 0. 0 square is 0. Half into 4 is 2 into minus 16. Now you see the minuses getting cancelled. 2 into minus 16 is okay. 2 into 16 is 32 divided by 100. Therefore, x square is 32 by 100. How did this become 2 by 25?
Sir, 4 by 5 root 2.
Wait, we'll come to that. But Vanilla, what mistake did you make?
Here I forgot to square 4. Like I forgot to square. So
Okay. Pawan, how much were you saying?
Sir, 4 by 5 root 2.
4 by 5. Okay, we'll just simplify this. This is 4 into 8. This is 4 into 25. Okay, so x square is 8 by 25. From that, you can get x as root 8 divided by 5. Root 8 is 2 root 2 divided by 5, which is same as 4 by 5 root 2 also. It's the same thing. Okay, and this answer is in meters. Fine. So proper solving you can do later, but understand what happened here. Initially, the spring block system was at rest with the spring at its natural length. We strike the block so that it gets some velocity to the left. As the block gets some velocity to the left, it starts compressing the spring. Okay, you can see in the right side diagram. This is the natural length of the spring. When the block moves to the left, the spring is in a compressed state. Then it starts exerting a force on the block. Due to that force, the block speed decreases, and it comes to zero somewhere, becomes zero somewhere. That somewhere is what we are finding out. Where that happens is what we are finding out. Okay. And in this process, we are using, like, to solve this problem, we are using work energy theorem, because in this process, as the block compresses the spring force is the only force doing work on the block. And in the expression for work done by spring force, the compression will be there. So that should give you the idea that maybe work energy theorem can give us the answer. Okay, let's consider another system. Just a moment. This one. A vertically suspended spring block system. Fine. So spring constant is K, mass of the block is M. Let's assume the block is in equilibrium. Tell me, should the spring be exerting any force on it or not? I think we had discussed this before also. If the block is in equilibrium, should the spring be exerting any force on it or not?
No,
Or
sir.
Rishi, tell me, what all forces act on this block? It's a vertically suspended spring block system. It's hanging. Okay.
The mass of it, then
Weight. You should say weight, not mass.
yes, sir.
Weight will be acting, and
Normal,
normal from where?
but won't it?
Normal force will act on an object when it is in contact with any other surface. What will exert normal force on this block, you tell?
No.
Okay, there won't be any normal force. What else?
Sir, tension
Tension exerted by?
by the spring.
Okay, so we call it spring force. That is what my question was. For the block to be in equilibrium, should the spring be exerting any force on it or not? Okay, Rishi, only tell which way will the spring be exerting a force on this block if it is in equilibrium?
Opposite to the weight of the mass.
Opposite to weight, so it will be in the upward direction. So spring force must be acting upward for the block to be in equilibrium. Otherwise, it's impossible for it to be in equilibrium. Okay, and don't call it as tension, just call it spring force. Okay, so the spring must be in a stretched state because only a stretched spring can pull. Compressed spring will push. Here, spring is pulling the block towards itself. So it must be a stretched spring. So assume this is the natural length of the spring and it's in a stretched state. Now you all derive an expression for this elongation. How much is the equilibrium elongation of the spring? Do it quickly. Type your answers in chat. What happened? It's a one-step answer. I didn't get one answer also. Okay.
X is equals to
Pawan, tell me. X is equal to?
X is equals to mg by k.
That's all. Okay. See, for the block to be in equilibrium, spring force must balance mg. So they should be equal. Expression for spring force is kx, where x is the elongation or compression. Balances mg. Therefore, x is equal to mg by k. When the spring is stretched by that much, the block will be in equilibrium. Aishwarya, did you understand?
Sir,
Yes,
but
sir.
the force is like variable now, so I have to integrate.
Vanilla, if the elongation keeps on changing, if the spring is moving, then the force is variable. And even if the force is variable, let's say the spring is moving, at one particular position, spring force will balance mg. At other positions, it won't balance. To calculate work, you will have to integrate force dot displacement, you will integrate. But here, that is not what you are asked, no? When it is in equilibrium, how much spring force acts on it? Or For the block to be in equilibrium, how much is the elongation of the spring is what you need to find out. So at that moment, how much is the elongation of the spring? That's all. Got it?
Yes, sir.
Okay. Fine. So when the spring is stretched this much, mg by k, the block can be in equilibrium. Okay. Now consider Consider a situation like this. Assume this is the natural length of the spring. Block is connected to it. And you release the system. Now tell me, at natural length, if you release the block, will it be in equilibrium? At natural length, if the block is released, like connected to the spring and released, will the block stay there itself? Will it be in equilibrium?
Yes, sir.
Yes, sir.
Okay, Rishi said yes. Pawan, what did you say?
No, sir.
No. Okay. Rishi, how do you justify your answer? How can you say it will be in equilibrium?
Sir, because only the spring constant is acting on it. So, and the natural length means
Wait,
it won't.
see, you have to speak, tell the terms correctly. Spring constant is not something which acts. Spring constant is a property of the spring. Tell properly, what is acting on the block?
Sir, the spring force and the
At
weight.
natural length, do you think spring force will act? If yes, in which direction does it act? Rishi, what is the formula for spring force?
Kx, sir.
Where x is?
The length of the spring.
No, x is not the length of the spring.
1 second, sir.
Okay, see, stay in touch with whatever we are discussing. One of you tell me, in the formula for spring force, F is equal to kx, what does x stand for?
It's the deformation, sir.
Deformation, elongation or compression. Now, when the spring is at natural length, there's no deformation. It has not been stretched, it has not been compressed. Then the spring won't exert any force. Pawan, why did you say the block will not be in equilibrium?
Sir, elongation అంటే పైకి స్ప్రింగ్ ఫోర్స్ ఏమి యాక్ట్ అవ్వట్లేదు సార్ ఉట్టి ఎంజీ ఒకటి యాక్ట్ అవుతుంది కాబట్టి
Yeah, because there is mg acting on it, it won't be in equilibrium. Okay, mg will pull the block down. Fine, and that's what we discussed in the last case, no? For it to be in equilibrium, the spring has to be stretched, and it has to be stretched by this much, mg by k. Okay, now keep this result in mind. And at an elongation of mg by k, the block can be in equilibrium. The block will be in equilibrium. Here, we release the block from natural length. We know that at natural length, it will not be in equilibrium because mg will pull it down. Because mg is pulling it down, the block will start moving down. But as the block moves down, spring force will start acting on it because the spring starts getting stretched. But for some distance, mg will dominate the spring force. Okay, because for spring force to balance mg, you need an elongation of mg by k. Anywhere before that, mg will be the stronger force. Okay, so weight will be acting on it. Weight will bring the block down. Let's assume this is the equilibrium level. Okay. So initially, when we released it, only mg was acting. Later, spring force and mg will both act, but mg will be the stronger force. So there will be force, a net force acting on the box like this. And when it comes to the equilibrium position, the net force becomes 0. Till then, a net force would have acted on it, which is the resultant of mg and spring force. So by the time it reaches this position, tell me, will it have gained any velocity, or the moment it comes to equilibrium position, it will stop? Will it be having any velocity at this position or not? Is my question.
Sir, velocity ఉంటుంది.
It will have some velocity because as it moves from this position A to this position B, along the way, it experienced a net force in the downward direction. So its speed would have increased and reached some value by the time the net force becomes 0. So what will happen? It will cross that position and go down also. Once it goes down below the equilibrium position, okay, once it goes below the equilibrium position, the spring will be stretched too much. Okay, at the equilibrium position, what is happening? Spring force exactly balances mg. At equilibrium position for that elongation, spring force exactly balances mg. Once you cross the equilibrium position and go down, the spring's elongation increases further, means the spring force will increase further, and mg will, spring force will dominate. Mg will be weaker than spring force. Then there will be a net force in the upward direction. Then the block will slow down, stop, but it will get pulled back by the spring. It will keep oscillating up and down. Are you all able to visualize this? Any doubts in this? Yusuf, did you understand? Are you getting the picture?
Yes, sir.
Okay. So anywhere above the equilibrium position, mg is the dominant force because spring is not elongated enough. But once you cross the equilibrium position and go down, spring force will be the dominant force because spring is elongated too much. Okay. So anywhere above equilibrium, the force will be in the downward direction. Anywhere below equilibrium, the force will be in the upward direction. And the further you go below equilibrium, stronger the net force in the upward direction. So it will keep oscillating. And if air resistance is present, gradually the speed will decrease, and the block will settle at the equilibrium position. That is what you see in a real life situation. In an ideal situation where there's no air resistance or any kind of friction, the block will keep oscillating forever. Okay. If there is air resistance and friction, which are anyway present in a real situation, oscillation will stop after some time. You all must have observed that happening. It may not be exactly a spring block system, but some objects or toys connected to springs, they will oscillate for some time and then stop oscillating. Okay. Right. I want you all to find out the velocity of the block, like it is released from natural length at rest. When it comes to equilibrium position, when it goes down by some distance, I want you to find out the velocity of the block. Derive an expression for it. Okay. I'll give you 3 minutes exactly. Make this, solve it quickly. There are no numerical values given in this problem. So the answer will be in terms of M, K, G, these things. Any answer, anyone? Okay. Pawan, how are you trying to solve this?
Sir, V square minus U square ఆ ఫార్ములా పెడతాం.
Tell the exact, like are you trying to use equations of kinematics?
అవును సార్.
When are equations of kinematics applicable?
When the acceleration is constant.
What is the guarantee that the acceleration of this block is constant? How did you confirm that?
సార్ అంటే డిస్టెన్స్ mg/k వరకే తీసుకుంటున్నాం అండ్ ఈక్విలిబ్రియం వరకు.
Distance is mg by k. Okay, correct. You know the distance, you know initial velocity, you need final velocity. How did you check or how did you confirm that acceleration is constant? Did you confirm that or not?
No sir.
Can any of you comment on this? Can any of you tell whether the acceleration of the block is going to be constant or not? The answer is there in the diagram itself.
It's not constant.
It's not constant. Why?
Because the net become like it's decreasing, of course.
Net force is decreasing. As the block goes down, the weight may be constant, but spring force is a variable force, no? As the spring gets stretched. Pawan, yes or no?
Yes sir.
So one force is constant, but the other force is variable. Therefore, the net force will be variable. And we had discussed all that. Initially, when the block is just released from natural length, the net force is mg. But later, the spring force starts increasing. So the net force starts decreasing. At equilibrium position, it becomes zero. The net force becomes zero. So the net force is a variable force. Acceleration also will be variable. You can't use equations of kinematics.
Here I got V as G into root 3m by k.
G under root
3m by k. Sir.
3m by k. Is this what you got?
Yes.
Okay, we'll see. Any other answers? Anyone? Fine. So, see, we have to discuss the idea first. How can we derive the final velocity? And the chapter name itself is an idea here. We are in the chapter work energy power. We'll apply work energy theorem. Work done by all forces is equal to change in kinetic energy. Okay. Follow me, all of you. And one of you unmute. Pawan, you only unmute.
Yes sir.
What all forces act on the block as it moves from A to B?
For gravitational spring force.
Weight, spring force. Any other?
Nothing sir.
No, these are the only forces. Therefore, work done by weight plus work done by the spring force should be the total work done. And that should be the change in kinetic energy of the block. This is the idea here. Okay. First thing we need to get an expression for is work done by the weight. Pawan, tell me, weight is a constant force or a variable force?
For constant force.
Constant force. How do you calculate work done by a constant force?
F into S.
Into another initial
F dot.
F dot S, Fs cos theta, you can say. The force is mg. How much is the displacement from here to here? Natural length to equilibrium?
mg by k.
Mg by k, we know that. Okay. So displacement mg by k. Angle between force and displacement?
0.
0. Cos 0 is 1. Therefore, work done by mg is m square g square by k. as the block moves from A to B. Hope this is clear to all of you. If you have any doubt in this step, you can ask. Okay. Aishwarya, you unmute.
Yes, sir.
Tell me the general formula to calculate work done by spring force.
Kx.
Kx is spring force. Work done by spring force is what I'm asking.
Sir, integral Kx dx.
Integral minus Kx dx. Okay. So minus integral Kx dx also, if you integrate, it becomes x square by 2. I'm writing it directly. We have to substitute the limits. Aishwarya, initial position, like at A, how much is the compression or elongation in the spring?
So 0.
0. It was at natural length. At B, how much is the when block comes to B, how much is the compression or elongation in the spring?
So x final.
How much? No, x final only. How much is that in this situation?
So mg by k.
Mg by k. So that's the upper limit for x. Substitute it. It becomes minus k by 2 into x square. So you have to square mg by k. It becomes m square g square by k square. And lower limit, if you substitute, you'll get 0. So the work done by spring force is minus m square g square by 2k. Why is the work done by spring force negative? Can any of you justify the minus sign? Why is the work done by the spring force negative? Answer is correct. It has to be negative. Why is it negative?
Yeah, because the force is opposite to the displacement.
Correct. The block is getting displaced in the downward direction, but the spring is elongated. Spring force acts in the upward direction. Block's displacement is downward. Since force and displacement are in opposite directions, the work done has to be negative, and we got it as negative. Correct. Okay, we are now in a position to find out that velocity. We got the work done by weight and the work done by spring force. Therefore, the total work done, sum of these two, m square g square by k, that's the work done by weight, positive work, minus m square g square by 2k, that's the work done by spring, should be equal to half m v square minus u square. U is 0. The block was released from rest. 1 minus 1 by 2 is 1 by 2. The 1 by 2 on the left hand side and the 1 by 2 on the right hand side cancel. You will be left with m square g square is equal to, okay, wait, m square g square by k is equal to mv square. 1m gets cancelled. The answer for speed is g root m by k. Vanilla, how did you get 3?
Sir, I only took the magnitude of spring force because you have to add all
Okay.
the work of one side.
See, we are adding the work, but one of them is doing negative work. Okay, okay, fine. So, is the solution clear to all of you? Any doubts in this? Okay. Fine. So let's move on with the chapter. I'll send you some more questions in the next worksheet. The next thing we need to discuss is potential energy. Last class we had discussed two types of forces called conservative, non-conservative. Okay. Can one of you tell me when a force is said to be conservative? Or what kind of forces are said to be conservative?
So work done must not depend on the path followed. So conservative.
If it's a conservative force, work done by that force should not depend on the actual path followed by the object. It should only depend on the initial and final positions. That's the overall displacement. Such forces are called conservative forces. That is one definition. We discussed one more point also. The work done by conservative forces in round trips is always 0. Okay. Now, potential energy, like as the name suggests, it's a kind of energy. First, okay, I want to hear it from you all first. Can any of you define potential energy? Or just tell what you know about it? What is potential energy, or what do you know about potential energy?
So it is the energy stored in an object.
Energy stored in an object. Kinetic energy also is energy in the object itself.
But like
The
this is
energy
You
due to
can
the force
stored in a
acting on
body
it.
by
wait.
virtue.
Let Rishi express his idea. Continue, Rishi.
This is like when there are forces acting on it, or due to like any external things acting on it. So
Okay, okay. Somewhat correct, but still not completely correct. Kinetic energy also is given to an object by forces acting only. When a force acts on an object and does work, it can give kinetic energy to that object. So that energy is also coming from an external force.
but this is stored in it, right? So it's not exactly moving or stored.
Kinetic energy is also stored only. Object is moving, but object carries that kinetic energy with it.
Oh yeah, yeah, makes sense.
Okay, okay. Vanilla, what were you saying?
The energy stored in a body by virtue of its position is known as potential energy.
Okay. Energy stored by virtue of its position. Fine, reasonable definition. We will refine that definition. Like, I'm sure since maybe 8th class or 9th class, you would have learned that definition itself. Energy possessed, okay, by an object by virtue of its position. Okay. Any other definitions, anyone? Fine. This is the most common definition that you might have learned in lower classes. Let it be. To some extent, it is correct only, but not the perfect definition. Do you know any formula for potential energy? Any formula that you might have learned in your lower classes? No? Okay, let it be. Not an issue. Can you suggest any situation where an object has potential energy? Or do every object everywhere, I mean, do all objects everywhere have potential energies? Fine, fine. So basically, potential energy, which we denote by the symbol U, capital U, is the energy possessed by a system actually, not one object. A single object or a single particle will never have potential energy. It's the energy possessed by a system of two or more particles or objects by virtue of its means the systems, okay, arrangement in space. Okay, so basically potential energy is that energy possessed by a system which changes based on its arrangement in space. Okay, if you disturb the arrangement of the system, the potential energy gets disturbed. And there is more to it also. This energy should arise from the conservative forces acting within the system. Arises from the conservative forces acting within the system. Okay, so you will talk about potential energy only when conservative forces are involved. And every conservative force has a potential energy associated with it, or every conservative force acting within a system can give or take potential energy from that system. Okay, anyway, see, this is just a definition. I'm sure you still didn't get any proper picture of it. Let us discuss this. Now you all must have heard this formula mgh. You all must have come across this formula mgh. Any idea where you might have come across this, or where you might have used this, or what this is? You never used this formula P is equal to mgh, potential energy mgh. Okay, fine. Let it be.
Sir, these are normally used sometimes for the bullet questions. I've come across those.
No, but what? Okay, potential energy is mgh. What is h? What is h in that formula?
Height, sir.
From where?
From the initial position, I think. I'm not sure. I don't remember.
Okay, okay. You see, Rishi, you should be very clear with your ideas. Okay, like from now onwards, you should never say, I don't know, or I'm not sure. Okay, study properly. You should be sure of what you are saying. Okay. Anyway, I'm telling this generally to all of you. At least tell me this. Last class we discussed which forces are conservative, which forces are non-conservative. Can you can you give me an example of a conservative force, anyone?
Gravity, sir.
Ha. Gravity is one. Is friction a conservative force or a non-conservative force? We had proved in the last class.
Non-conservative.
We proved that it is a non-conservative force. Okay. And you solve the worksheet, you'll understand that spring force is also a conservative force. So for now, out of all the forces that we have discussed till now, gravity and spring force are the conservative forces. So you can define something called gravitational potential energy. And you can also define something called spring potential energy, which is more generally called elastic potential energy. Okay. And as Rishi was saying, potential energy is a kind of energy which can be stored in the system and it can be retrieved also. Fine. We'll discuss all that, like as we derive the formulas and apply them, you'll understand. So remember, potential energy is the energy possessed by a system of two or more particles or objects by virtue of its arrangement in space. So it depends on how far the particles are. Okay, if there are multiple particles, then exact shape in which they are arranged, it depends on all of that. If you change the arrangement, you bring the particles closer or take them farther, the potential energy could change. And it arises from work done by conservative forces. So arises from conservative forces means the energy is given or taken by conservative forces only. acting within the system. Now the conservative forces we have discussed so far are gravity and spring force. Okay. So we can derive a formula for potential energy that arises due to gravity. And we can also derive a formula for potential energy that arises due to spring force. But we need to know how to derive the formula for potential energy. Now the basic idea, by definition, change in potential energy of a system. Okay, delta stands for change, U stands for potential energy. Change in potential energy of a system is negative of work done by conservative forces within the system. So when conservative forces do work in a system, they can give or take potential energy away to or away from the system. So remember, potential energy is related to work done by conservative forces and only conservative forces. Okay, it's a quantity we associate with conservative forces. Fine. So we are now going to use this definition, negative of work done by conservative. We are going to use this definition to derive a formula for the potential energy in case of gravity and also in case of spring force. Okay. So I want you all to note down this formula. Change in potential energy delta U is negative of work done by the conservative force. Okay, hope you have noted. Now, let's first derive an expression for gravitational potential energy. Consider the Earth and an object close to the Earth. See, according to Newton's law of gravitation, every mass attracts every other mass with a gravitational force. Okay? You are attracted by all the objects around you. All the objects around you are attracted by you also by gravitational force. But do you feel the gravitation of those objects? No. The only significant gravitational force we feel is that of the Earth, because the Earth's mass is so huge that the force exerted by it becomes significant, can be felt by us. Okay. So for now, we are going to consider Earth's gravity and the potential energy that arises due to it. Okay. Assume this is the Earth and consider an object on the Earth, maybe somewhere here. Let its mass be small m. Okay. So when you go out of the Earth, like when you go into space and look, this is how it may look. Earth and an object. In fact, the object size won't even be perceptible compared to the Earth's size. For us, things appear like this. Earth's surface appears flat for us. Okay, because we look at like when we look around us, we can only see a small portion of the Earth's surface, and a small portion of a curved surface is always appear. Okay, there was an interruption in the connection. Are you all able to see my screen?
Yes, sir.
Okay. Right. So assume this is the Earth's surface, so ground. And let's say there's an object. Object size will always, obviously be very small compared to the size of the Earth. Let's say there's an object somewhere here whose mass is m. Assume it is initially at a height h1 above the ground. Okay. From this position, okay, you may call this position as A. Let's take the object to another position, to a greater height, maybe somewhere here. Okay. the initial height of the, just a moment. The initial height of the object from the Earth's surface, like from the ground, is h1. And from that height, let's say it is taken to a new level, new position B, where its height from the ground is h2. Height above the ground is h2. Okay. Now this particle is always attracted or acted upon by the Earth's gravitational force. Now you know gravitational force is a conservative force. So if you consider the Earth particle system, okay, assume Earth and particle as one system, then gravitational force of the Earth or the gravitational force between them is a conservative internal force to this system. Okay. And if this force does any work, it results in a change in potential energy of the Earth mass system. Okay, it's not potential energy of only that mass. Earth plus mass, if you take as one system, that system's potential energy changes. Okay, and we have a definition. By definition, change in potential energy of a system is negative of work done by the conservative forces acting within the system. Now, for the Earth mass system, the conservative force acting within the system is gravity. So we have to find out work done by gravity in this process to get an expression for change in potential energy. And work done by gravity is not a big deal. This is the displacement of the object, and its weight mg is acting downward. That's the force whose work we have to calculate. So one of you tell me, is weight a constant force or a variable force?
Constant.
Constant force. Work done by constant force, F dot S, Fs cos theta. So work done by mg, that is gravitational force in this process, the force is mg. Can any of you tell me the magnitude of that displacement?
H2 minus H1.
H2 minus H1, correct. An angle between them?
$180.
You can see in the diagram, they are opposite to each other. 180, cos 180 is minus 1. So when the object is taken from an initial height h1 to the final height h2, this is the work done by gravity. And if this is the work done by gravity, which is basically a conservative force, we can say that the change in potential energy during this shifting of the mass, we can say that the change in potential energy is negative of work done by mg, and negative and that minus 1 will cancel. You will get the answer as mg into h2 minus h1. Okay, so what have we derived now? We have derived an expression for the change in gravitational potential energy when an object is raised to a certain height above the ground. Mg into h2 minus h1. So this is the proper formula for change in gravitational potential energy. Suppose h1 is 0. Or see, ultimately it depends on the height by which the object rises. Okay, the extra height by which it rises is what matters. Whether it rises from h1 or it rises from some other level, by what extent it rises is what matters. Fine. So you can write the formula for change in gravitational potential energy as mg into delta h, actually, the height by which something rises. And if delta h is positive, the change in potential energy will be positive. If delta H is negative, the change in potential energy will be negative. That means if height increases, potential energy increases. If height decreases, potential energy decreases. So here you see it making sense. If you change the arrangement of the system, you increase the height of the object or you decrease the height of the object, then potential energy changes. That is why, or that justifies the definition that potential energy depends on the arrangement of the system. Okay, so when you are taking an object away from the earth or towards the earth, you are changing the arrangement of the earth mass system, and that system's potential energy will change. You can say it's the particle's potential energy that is changing, that's fine, but actually it's the earth and particle system's energy that is changing. Okay, but loosely we will say it's the object's potential energy that is changing, but you must remember that potential energy is never for a single object, and this mass gets some potential energy because of the gravitational force exerted by the earth. Okay, so potential energy does not belong only to that mass, it belongs to the mass and earth system. And when you lift an object to a certain height, its potential energy changes by mg into delta H. Therefore, if an object moves upward, or okay, we'll properly write it. If the height of an object from the ground increases, its potential energy increases, and the reverse. If height decreases, its potential energy also decreases. Okay. Now, suppose I call this as zero height. Actually, the initial position is not at zero height, but let's say I call it as zero height. And let's say I call this height as h. Then tell me, can we say potential energy is equal to mgh or not? If the initial level is assumed to be 0 and final level is assumed to be h, can we say the potential energy is mgh or not?
Yes, sir.
We can. Okay. So usually what they do is they assume ground level to be 0 height, and any height above that they take it as h. But there's no rule like that. You can assume any level to be 0 height while solving a problem. Okay, and above it any height will be considered as positive, below it any height will be considered as negative, and that will give you the potential energy directly. Okay, we'll solve problems, you'll understand. So remember, potential energy is never for a single particle, it's always for a system. Here we are discussing the potential energy of earth and mass system, but you can loosely call it as potential energy of the mass itself. Okay, that object. And when you increase the height of that object from the earth or decrease the height of that object from the earth, its potential energy changes, and it can be calculated using this formula. Okay. Solve one question. You can try to answer this directly. A 5 kg object initially at a height of, let's say, 2 meters above ground is taken to a height of 8 meters above ground. Okay, both heights are given with respect to ground. How much is the increase in its or change in its potential energy? Simple calculation, 5 kg object initially at 2 meters is taken to a final height of 8 meters. how much is the change in its potential energy? I got one answer as 3000 and two answers as 300. Okay. A direct formula mg into delta H. Mass is 5 kg, G is 10 as always. The change in height is 6. 13 to 10, 300 joules is the answer. Okay. So depending on how much an object is rising or falling, you can tell the change in its gravitational potential energy. Okay. Expression for spring potential energy we'll discuss in the next class. But now we'll discuss another important, not important, I mean, one of the most important laws in physics in your syllabus. Law of, notice down all of you, law of conservation of mechanical energy. Law of conservation of mechanical energy. Okay. You first need to know what mechanical energy means. Very simple. Mechanical energy is the sum of potential and kinetic energies of a system. That's all. Both of them put together are called mechanical energy. Okay, put together is called mechanical energy of the system. Fine. Now, law of conservation of mechanical energy. Basically, it tells you when the mechanical energy of a system remains constant. We had discussed law of conservation of linear momentum. Can one of you tell me the law or the condition when linear momentum is conserved?
Definite equal
Infinite
to
equals
0.
0.
Good, good. Pawan Vanilla. If the net force on a system is 0 in any particular direction, then the linear momentum of that system in that direction does not change. That is law of conservation of linear momentum. Similarly, we have a law related to mechanical energy. Okay, not exactly the same condition, but conservation of mechanical energy means under some conditions, mechanical energy of a system won't change. That is what we will discuss here. Mechanical energy, as I said, is potential energy plus kinetic energy. And last class, and maybe the class before that also, we had talked about conservative, non-conservative forces. And I was telling you, conservative forces conserve something, they preserve something. Okay, this is what they preserve. Conservative forces cannot change and will not change the mechanical energy of a system. Okay, non-conservative forces can do that. Basically, that is the definition of conservative force. Conservative force, what is it conserving? Mechanical energy it is conserving. Such forces are called conservative forces. If they convert mechanical energy to some other form of energy, those forces are called non-conservative forces. And for that, scientists performed calculations and all, and they came up with those explanations. Conservative means in a round trip, it has to be 0. Work done should not depend on path. Okay. Those kind of forces don't or cannot change mechanical energy of a system. Okay. And from calculations, they even found that if the work done by a force depends on the path, such a force will change the mechanical energy of the system. So they call those forces as non-conservative. Okay. Fine. Tell me the different forms of energy that you know. Kinetic energy is one, potential energy is one. Tell me some other forms of energy.
So light, electrical, chemical, so many.
Light energy, chemical energy. Okay. Aishwarya, tell me some forms of energy that you know.
Sir, tidal energy.
Tidal. Okay. So the energy of water waves. Basically, that is kinetic energy only, the energy with which water moves. Okay. So it's not a different form of energy. It comes under mechanical energy. Any other?
Geothermal energy.
Geothermal energy. What is that? I mean, I think I heard of it, but can you tell what it means?
Sir, the energy that's produced due to the heat produced underneath.
Okay, fine. So heat energy, basically. It's a form of heat energy. Okay, good. Heat is a form of energy. Any other forms of energy, anyone?
Sir, electrical energy.
Electrical. Okay. Any more? Okay. Sound is a form of energy. And magnetic energy is there. Nuclear energy is there. Okay, there are many different forms of energy out there. Okay. Right. One of you tell me law of conservation of energy, the law that you had studied in your childhood, or maybe in 10th class also, I think it is there. What is the general law of conservation of energy? Okay. See, energy can neither be created nor be destroyed. Have you all heard this before or not? Energy can neither be created nor be destroyed. Means you cannot change the total energy that is there in this universe. But it can be converted from one form to another. Okay. This is the general law of conservation of energy. The total energy in the universe does not change. You can't produce new energy. You can't destroy existing energy. You can only change it from one form to another. Let us discuss this a little bit. Can any of you tell me any situation or any machine or anything where, or any process where one form of energy gets converted to another, or one form of energy is used to produce another form of energy? Okay. What does a bulb do? Light bulb, what does it do?
Sir, electrical energy and light energy like marks.
Correct. Bulb converts electrical energy to light. So it's a device which does an energy conversion from one form to another. Okay. What does a fan do? What kind of energy does a fan consume? Okay, we all know that electrical energy is consumed by it. And what kind of energy does it convert it into?
Sir, wind.
Wind. Okay. You can say mechanical energy. It moves air molecules. It gives kinetic energy to air molecules. So electrical to mechanical. Like tidal energy, one of you said, wind energy is also a kind of mechanical energy only. Okay. What does a vehicle engine do? Let's assume a petrol engine, not an electric vehicle. The engine of a petrol vehicle, what does it do? What does an engine consume, or what does a vehicle consume?
Sir, ఆయిల్ తీసుకొని మెకానికల్ ఎనర్జీలో కన్వర్ట్ చేస్తారు.
What does it take?
Fuel.
Fuel. Okay, it consumes fuel, converts it into mechanical energy. So what kind of energy is getting converted to mechanical energy? What energy does fuel have? Fuel has chemical energy. That is first converted to heat. Okay, fuel undergoes combustion inside the vehicle engine. That's why the engines are called ICE, internal, I think internal only, internal combustion engines. Okay, or is there any other full form? They are called ICE engines. Just a moment, let me confirm. Yeah, internal combustion engine. So the fuel undergoes combustion, heat is generated. That heat is used to produce mechanical energy. So there are two steps of energy conversion that happen in a vehicle engine, combustion engine. Okay, see, there are many devices or machines which convert one form of energy to another. These are common. Okay, and the law of conservation of energy states that you can neither create nor destroy the existing amount of energy in this universe. So one form can be converted to another. Now we are discussing law of conservation of mechanical energy, particularly this one kind of energy. When will it remain conserved is law of conservation of mechanical energy. And I kind of told you the condition already. Conservative forces cannot disturb mechanical energy of a system. Non-conservative forces can disturb the mechanical energy of a system. So can any of you try to come up with a statement? When will mechanical energy be conserved? Can you think of a statement for the law of conservation of mechanical energy? By that time, I'll write it here. Conservative forces cannot disturb the mechanical energy. Non-conservative forces can disturb the mechanical energy. So, when will mechanical energy of a system not change? Okay, simple thing. If conservative forces are the only forces doing work on a system, then its mechanical energy won't be disturbed. Okay? Non-conservative forces have to do zero work. Then mechanical energy will not be disturbed. That's all. That's the statement. So if work done by non-conservative forces on a system is zero. Okay, the total work done, they may be doing work. Suppose there are multiple non-conservative forces. One non-conservative force does positive work. It will increase mechanical energy. Another non-conservative force does negative work. It will decrease mechanical energy. Okay, so that is allowed. The individual non-conservative forces may be doing work, but the total work done by all the non-conservative forces put together should be zero. Then it means the system's mechanical energy is conserved. Okay, this is the statement, and next class and few classes after that, we will be working on application of law of conservation of mechanical energy. This is one of the basic things that we will try to apply in many situations from now onwards. Wherever conservative forces are involved, we'll see if mechanical energy conservation can be applied. That will help us in solving the problems quickly. Okay, so one of you quickly tell me what is meant by mechanical energy of a system. What is meant by mechanical energy of a system?
The potential energy plus the kinetic energy.
The sum of potential and kinetic energy is put together is called mechanical energy of the system. What kind of forces can change the mechanical energy of a system?
Conservative forces. Right?
You told the exact opposite answer. It is written here, conservative force cannot disturb mechanical energy. I asked you what kind of forces can change mechanical energy. The answer is non-conservative. Okay, fine. So in a process, in a certain displacement or in a certain what do you call rearrangement of a system, if the work done by non-conservative forces is zero, then you can say that the system's mechanical energy remains conserved. And how do we apply this? Can one of you recollect and tell me, how did we apply momentum conservation? I'm not asking in which situations we applied, but how do we write the equation for momentum conservation? Momentum is conserved, means it does not change, means initial value is equal to final value. So we used to write P initial is equal to P final. Similarly, for mechanical energy conservation, once the condition is satisfied, you write initial mechanical energy of the system is equal to final mechanical energy of the system. Therefore, we apply it this way. Sum of initial potential and kinetic energies is equal to the sum of final potential and kinetic energies. That's all. Okay, next class we'll see how to apply this. And see, the classes following this one are very important. If you are very confident about mechanical energy conservation, then it's your choice, but otherwise attend the classes without fail. And tell me, next class will be when? On Saturday, no? Saturday, can you attend 6:30 to 8 like today?
Yes, sir.
Okay, those of you who cannot attend, tell me now. Saturday, 6:30 to 8.
Sir, I have class tomorrow.
I didn't understand.
I too cannot attend, so.
Okay, okay. Fine, then we'll start at 7 o'clock itself. But 7, you should be able to attend. Okay, if possible, I'll take from 7 to 8:30 or 7 to 8 on Saturday. Maybe another 1 hour on. Wait, just a moment. What day is today? Friday, no? Sorry. Saturday is tomorrow. No, I was talking about Monday's class only. Monday, can you all attend? 6:30 to 8.
Yes, sir.
Yes, sir.
Okay, anybody who cannot attend 6:30 to 8 on Monday? All of you can. Okay. Right. Next class will be on Monday itself. I was thinking today is Thursday and next class is Saturday. No. Right. And I will send you another worksheet. Make sure you solve the worksheet and send the answers back to me. You have 2 days, Saturday, Sunday should be able to solve. And the worksheet that I sent yesterday also. Okay. Answer those questions and send it back to me. Okay. Thank you all. We'll continue on Monday.
Thank you, sir.